props to him. Throw him a couple of bucks. Everything he makes is great. Furthermore, John Sterling, Carl Anguli, and Favonia. I work with them on QuiltTT, and a lot of the ideas from the later portion of this talk are pretty much stolen from them directly. So just want to make sure that they get their credit when credit is due. So get a broad look at the plan here. First, if we want to talk about tactics, we need to know what even is a tactic. And after that, kind of drill into how some of the stuff you just saw works underneath the hood, implementation strategies there. And after that, I just kind of want to talk a little bit more broadly about where we can go from there, and some of the cool things we've been looking at recently. So what even is a tactic? So the 10,000-foot view, for me at least, is that before I get into this, actually, if anyone has a question, please just shout out and say, I have a question. I'd be more than happy to answer. Otherwise, I'm just going to assume that everyone totally understands exactly what I'm talking about and steam on. So please, if you are lost, say, I'm lost. Anyways, back to what I was saying. The sort of 10,000-foot view is that a tactic is a composable means of solving some problem. Specifically, thought I had a little bit more on there about this, but just talk off the cuff. Specifically, if you have something like program synthesis, right? We want to be able to basically build a program by taking little tiny looks at our current state and saying, well, if I knew how to solve these smaller problems, I'd be able to make a solution to the big one. But this sort of idea isn't necessarily limited to program synthesis. And later on, we'll look at a couple of other examples where the sort of same problem is there, just with a different can of paint on it. So let's take a look at a concrete example, which you should all be very familiar with, which is writing Haskell programs. This one may look a little bit contrived, but how would we go about writing this function? Well, there's sort of only one obvious move to make here, right? Which is we got to bind some stuff. We got to introduce a lambda. And then after that, it's well, there's really only one obvious thing we can do here, which is, introduce a pair constructor. Furthermore, if we want to make an A and a B, there's really only one way to make those, which is to sort of apply the functions we have in scope. And then finally, we can use the variables to fill in the holes. And there's a reason I've bolded those guys. But this is really just a mechanical decomposition of the problem, right? At sort of every point in this process, we're just sort of looking at the whole, looking at everything we have in scope, and then going, aha, we can make one step and produce some new holes. So there's really not really that much thinking going on here. So the big idea here is that we're going to write some very small composable pieces that can decompose the problem down sort of one step, right? So in the example before, we have something that can introduce a lambda, right? Or we can have something that can take, we want to produce a pair, break the problem down into two problems, and then sort of glue those solutions back together to get a solution to the bigger one. Or if we're trying to produce something, we might need to apply a function. No, our tactics do not have types.
So it's more like, so is it more like an untyped MTAC, or?
It's closer to, well, they kind of do, kind of don't, but it's very much MTAC, LTAC inspired.
Has it will backtrack and try different case branches in LTAC.
Yes,
so,
we do have lots of backtracking in search.
Programming meets runtime type errors.
Yeah, basically. You do have to be a little careful, but
it's really cool that once you it's poorly explained in most cock prover material. But that's the real secret sauce behind some of the more effective cock tactic automation, like the stuff Adam Tripala popularized.
Yeah.
That you basically can try different decompositions, and they're just different matching expressions. Or they'll do the same matching expression, just at a different point.
Yeah, yeah. No, this whole perspective of all we're doing is just decomposing down the problem is super valuable. And in my opinion. It's kind of the way to think about it. And yeah, you can run very far with it. This wasn't. Oh yeah, so there's sort of these little atomic pieces that kind of do one tiny step of the problem and maybe potentially produce new problems that we have to solve. Now that we have these sort of atomic bits, let's start producing molecules by composing these together with combinators, right? So we can have something that, say, takes a tactic and then runs another tactic on all the sub-goals that it produces. Or we can say, hey, run this tactic, but also run this tactic, and sort of combine together all the solutions. Or we can say, hey, here's a tactic, just run it over and over and over and over and over until it fails. Or run all of these tactics and sort of interleave their results fairly. I will get to that, Emily. Basically, there's a whole section here on how exactly these things compose. So it's a little bit involved. Anyways, we can sort of use these to build like automated solvers, right? So here's a crappy little example that's in one of the test cases, which is sort of to solve a problem, you just try and apply lambda, like the lambda tactic a bunch of times, and then you try and split it if it's a pair, or we try applying some function and then recurse, or you just use some variable in scope. And just kind of keep going until either there's no solutions or you find a bunch of solutions. But this is really easy to write. All you needed to do was write all these little individual pieces that kind of just like, oh, can you synthesize a lambda? Or, oh, can you synthesize a pair? And then just glue them together. It's sort of like parser combinators, but they're automated theorem proving instead of parsing expressions. This isn't just limited to program synthesis, by the way. This sort of pops up in all sorts of places. For example, we could think of like an algebraic simplifier, right? You can write that using tactics. You have like a commute tactic or a reassociate tactic, and then you glue all these together, and then you essentially get an engine for performing algebraic simplification. Or like symbolic integration or differentiation, right? You can have an integration by parts tactic, which takes an expression, does that, and produces some new poles or integrals that you need to solve, right? It's sort of that same process of iterative refinement of the problem down to little pieces that then we can then sort of easily solve. Of course, elaboration and proof assistance, which we will talk about a lot more in a later section, but essentially you're trying to take some source language, right? And then produce some core language that's got all the details filled in, right? And that's sort of the same instance of this problem. We can kind of elaborate bits of it, we can glue those all together to get a big thing that can elaborate the whole darn language. So now that sort of, I guess, take a breather here, do we have any questions? I know I'm moving pretty fast, so I don't want to leave anyone in the dust.
So the tactic language as you're laying it out looks like it overlaps similarly in style with the design the lean folks kind of articulate as what they're doing these days for like the core tactics.
The one that I presented there does look a lot like leans, but the idea of tactics is not necessarily attached to that
at all. Trying to point out other concrete ones for those who are curious, so that there's like an easier corpus of intelligible examples.
Yeah, Isabel has a lot of really interesting sort of combination tactics. Yeah, Isabel's got some great ideas in there. More people should look to it for inspiration. Coq famously has like 20,000 different tactics libraries. I think MTAC is the good one these days.
Isn't like, is the current style in Coq still like basically SS Reflect influenced, or has it shifted?
I don't really keep up too much with the state of the art there, but I think it's SS Reflect.
And then theoretically MTAC too, but
yeah.
I think now working on the guy behind that's working on a Ruby sibling crystal right now.
Did not know that. And yeah, there is sort of one other idea that we'll discuss later on that I think is pretty cool, but I don't want to spoil the fun. So does anyone else have any sort of questions, or is like, I am totally lost with what he's talking about? Okay, if not.
I missed some key moments there, so I guess I'll have to watch the recording and if it's going to be made public.
Yeah, I think the recording is going to be made public. Though Sean might speak to that a little bit more. Yeah, we can arrange that. Okay. There's nothing else. I'm just going to assume that we're good and steam on ahead. So this is sort of the 10,000 foot view. Now let's take like the sort of 10-inch view of specifically how does this work inside of HLS. We can use this sort of exact same process of like goal decomposition that we alluded to earlier, but there's an extra twist. Oh, someone say something?
No.
Oh, sorry about that. So Emily, here's the answer to your question. Here, we need to think about sort of how tactics compose if we want to have a good story for implementing them. So as a general mantra, if you want to design something, you should look at the composition first. And that should be your primary focus. And then all the implementations should sort of lead from there. If you have something awesome and great, but it composes like crap, then you don't have something awesome and great. To do that, let's sort of take a small case study and look at some very stupid code that you would never write, but it's still interesting from this perspective. So we're taking two things, we're trying to make a pair. So note that context matters here for this whole, right? So the thing we're trying to produce isn't just an A and a B. It's an A and a B where we have an A and a B in scope.
Is that with the implicit for all A, B in the type signature, or A and B in from a parent scope binder?
Implicit for all.
Okay.
It doesn't necessarily matter, but just say it's implicit for all. I should have put that in there. That's a good point. So when we're trying to synthesize something, our goals aren't necessarily types. They're types in a context, right? So there's a bit of notation here, in case no one's familiar with this. The type theoretic notion here, or notation, is gamma turnstile A means we have some context, gamma, and then some type A in that context. So the example before would be we have an X of type A, a Y of type B, and we're trying to produce a pair of A and Bs. So how does a tactic like split behave? And for context, split is the one that takes the goal of a pair and decomposes it down into two goals, one for each side. Takes a goal of form, gamma AB, and produces two new goals, gamma A, gamma B. And then, once these goals are solved, so we've synthesized an A and we've synthesized a B, we sort of take those two solutions, we glue them together, get a pair constructor, and then sort of produce that as our extract from the tactic. I like to visualize these as sort of a tree, which becomes helpful when you have really complicated situations. So sort of an gamma AB comes in the top, and that split tactic sort of splits it apart into two new goals. Let's say we had some other tactic tau, and then we wanted to compose that onto this tactic. How does that work? What's sort of the natural composition behavior here? Well, you take tau, you take the sub-goal that's produced by split, each one of those, and then you feed that into our tactic tau, and then see what sub-goals it produces, and that produces a whole new tactic. So of note is that this composition is monadic. So if we think about these goals here as our sort of A's in the monad, a tactic takes in sort of an A, or a goal as an input, and produces a bunch of new goals. And then when you bind, you take your new tactic and sort of glue it onto all of those other goals, and you get another one. And this is important. So if anyone's lost here, say, I am lost. Because
so that's for applying the same tactic to all of the results.
yes, that is sort of the natural notion of composition. of two tactics is you take the first tactic, you run it, and you take the second one and apply it to each one of the goals produced by the first one. And
Won't
then,
the goals usually be unrelated or no?
I mean, if tau is something like auto, it could solve them.
Forward or backward chaining right now?
So it's forward and backwards chaining. We're forward chaining the goals, but we're backwards chaining the things we synthesize.
Okay.
So it's sort of, the information flows all the way down to the leaves, and then once we've solved those, it sort of flows all the way back up to the top, and we glue all the bits and pieces together to get our final results.
Okay.
So that sort of dual information flow is actually quite important. And we'll see that a lot when we actually get into the sort of toy implementation I have here. So yeah, this thing here where we sort of glue and feed all of the goals produced by the first guy into the second guy. Yeah, that's a cute perspective, actually. I'm going to steal that. Thank you, Emily. So bind is this guy where we sort of feed into that second tactic. And pure looks something like this, where you have a goal. Pure just says, I'm going to produce one sub goal. It's the same thing. And then when that guy gets solved, I'm just going to feed the solution straight back up. And you can check the laws. We have a bunch of quick check tests that check these laws for us in the implementation, and they're good. It's worth noting that this is not my original idea. This was taken from a paper by John Sterling and Bob Harper called Algebraic Foundations of Proof Refinement. So it's a great read. Really fantastic stuff. Can't recommend it enough. So okay, we've got our composition behavior sort of figured out. How do we actually implement this? The really naive way of doing it is you have sort of two functions, right? One that decomposes the goal into lots of smaller goals, and one that sort of glues those solutions back together. But this is kind of bad in a couple of ways. First of all, you can't witness the monad instance because goal shows up in both covariant and contravariant positions. And composition is just like a total bear to write because you need to stitch together all these lists and blah, it's not very good. So this is a fine mental model, but we need to do something better. And we can do better. So consider the following type. So subgoal is something that we want to produce a goal. And when we do, we're going to take the ext, which is short for extract, the thing we're synthesizing, and we're going to produce some new goals after that. And then we repeat this until we're done with the solved constructor, and that's going to be sort of the thing we finally extract from a tactic. And of note is this actually solves a big problem with tactics, which is sort of dependent subgoals. So if you don't know too much about proof assistance, don't worry about this part. You can kind of tune it out. But when you're trying to produce something like an existential or a sigma type, you end up in a weird situation because the type of the second subgoal depends on the value you synthesized for the first. And this shows up in quite a few contexts. And it's a bit fiddly to get right. But this sort of continuation style totally solves it, right? Because you can just change the second goal you produce because you have your hands on the extract of the first. And if the first one doesn't get solved, you just get fed a hole, and then you go, okay, well, I'm just going to produce a goal that has a hole living in it now. So yeah, it totally solves that problem. Okay, turn off the proof assistant talk for now. Get back to the implementation, but yeah, this is sort of the key insight here, this type. And then we define a tactic as such. It's something that takes a goal and then produces something that can then ask for a bunch of sub-goals and then group together all those results and then finally produce a result out the top. Does this make sense to everyone so far? Is this type hurting people's brains? Okay, I'm going to take that silence as we're good. Steam on ahead.
Definitely fine, but definitely some people will need to look up CPS of things later.
Yes, the Sandy and I had our brains melted by CPS. I don't even know how many times during the implementation of this. It does hurt your brain.
Then everything becomes easier.
Yes.
Like literally every wacky thing becomes a way easier thing. So this is like both kind of free and CPS-y.
Yes, it's in the implementation. We have a bunch of other constructors for doing sort of fancier bits, but essentially you have this giant initial thing with this one CPS bit in there that sort of makes all the magic happen. And interestingly enough, this looks a lot like pipes. So there is a monad instance hiding inside of pipes that Gabrielle missed. Yeah, this is pipes. Secretly pipes.
It looks profunctory a little bit.
Ish. There is a profunctor instance that we'll get to. But yeah, there's some cool stuff in here. And this is sort of monadic in Goal as well. The implementation of that instance is a bit hairy, but it's sort of the thing I was describing earlier, where you sort of chain on each of those proof states. Oh, that's sick, Emily. I'm gonna need to talk to you about that later. That would be very cool. That's a great title for a paper right there. So we have our definition of a tactic, but how do we write something like split? All right. So we've been kind of thinking about how tactics compose, like, quote unquote, externally, but we really need to think about how they compose, quote unquote, internally to make sense of this. Like, and this doesn't make any sense until, you know, I sort of hand wave it, but we've been thinking about how basically we feed together goals and solutions and all that, or we sort of chain goals and solutions to those goals, but we don't know how to sort of group together solutions into bigger solutions. And this is the sort of internal aspect of it. So if we go back to this square diagram, the tree, we know what's going on the outside, but we don't know what's going on inside of that split box. We don't actually know how to implement that yet. Essentially, we want two functions, right? The first one, subgoal, says, you give me some goal that you want to produce, and then I'll, you know, do whatever. And then once I'm done, I'll give you the sort of solution to it. And then we want the second one, which takes something that, you know, takes in a goal and produces a solution and turns that into sort of a tactic. The name rule is sort of meant to prod you to the fact that your tactic should sort of be the atomic judgment rules of your type theory, but don't worry about that. And the key realization, and this is the last piece of machinery, is that this is basically the same thing as proof state from before, but instead of focusing on that goal bit, we're going to focus on that extract bit. So let's puzzle over this type. So we're going to be monadic in A here. So we can implement that subgoal function from before by just saying, okay, freely produce a subgoal, and then take the extract and then say, yeah, we're solved. Bind will kind of work over this solved constructor here and kind of chain things on horizontally. And then rule basically just realizes that this data type here, which inside of the actual implementation is a new type over proof state, is basically just proof state and then turns it into a tactic. So this last little piece, this is how we actually write the sort of primitive atomic tactics as opposed to the sort of bigger combinatory tactics. So here's an example of what one of these things looks like once they're all done. We have types, we have terms. A goal is, you know, basically just some context full of types, and then a term that takes variables from those. And then split is a rule. We match on the, you know, thing we're trying to, the goal we're trying to synthesize. If it's a pair, we just call subgoal twice. and then block out a tuple out the ends, and then don't worry about this unsolvable thing. Yeah, if it's not a pair, you just throw an error, basically. And that's it. So all the primitive tactics are like these teeny tiny, like 8 or 9 line functions, which is pretty slick. Now, this library refinery essentially provides you a toolkit for designing your own tactic systems for your language. So basically, it takes these types I've showed you before, these rules and the proof states and the tactics, makes them totally generic over, your goals, the things you're trying to extract, your errors, your state, yada, yada, yada. So all you need to do is implement a couple of type classes, build your atomic sort of tactics using this rule construct, and then you kind of get the rest of the system for free. Like I have an example for simply typed lambda calculus, an automated solver for simply typed lambda calculus, and it's like 100 lines of code. And that's including defining the types, defining terms, defining all the atomic tactics, and defining the solver. I think that's pretty cool. And the implementation does have a couple of points of divergence from what I presented here. Namely, the more type variables, a couple of these things have like 9 constructors instead of 2. But the core idea is the same. And if you went into the implementation with sort of this presentation in mind, hopefully you'd be able to read it and understand it.
You use this in your type theory?
We don't. We use the next section, which is called "Where Can We Go From Here" in our type theory. So this is sort of what I was thinking about last year, and this next section is what I've been thinking about over the past couple of months, and specifically what John, Carlo, and Favonia have been thinking about for a lot longer. So I definitely want to give them credit for those ideas. But yeah, this refinery library is what Wingman uses internally. So every time you saw those solutions and everything, this is how it works. So it may look like magic, but it's not magic. It's 2 types, a bunch of combinators, and a bunch of CPS. And that's kind of all there is to it. So does anyone have any questions before we move on to Reed's overarching vision of the future of yes, that SLTC critter is inside of the refinery repository. I think it's under the test or example directory.
How fast is it?
It's okay. There's some things I would like to change. So one of the problems with, or not problems, one of the difficult things about synthesizing Haskell code is that you're not necessarily only trying to produce something of a type. You're trying to produce the right implementation for a type. So for instance, if I had some function, I don't know, that had 2 A's and there was a monoid instance for A, right? There's a stupid implementation where you just use one of the A's and then don't do anything. So it's essentially const. And that's not the right answer. Or anything that returns a list, right? There's always a trivial answer where I just return the empty list. And that's technically an implementation of the type, but it's not the one that you want. So the solution we have to sort of figuring out what the correct one is we synthesize a bunch of implementations. And then we have a bunch of heuristics that look at the implementations and say, okay, did you use all your variables? Did we case split on something twice? That'd be kind of dumb. Sort of things like that, where we can take a more global view of the thing we've synthesized.
So that's kind of like some of the tactics tools that like Idris 2 does.
Yeah, so it's a lot easier if your type system provides you that information. Like if you have linearity, obviously it becomes a lot easier to not synthesize things that are just const. And linear Haskell does exist, but it didn't exist at the time of writing this, and you can't necessarily ask for everyone to write linear Haskell just to get tooling. And if you have dependent types, it obviously gets a lot easier because you can restrict the search space down even further. But we wanted something that could sort of work on most reasonable things. For instance, most of the time you're writing functions, you want them to be homomorphisms, right? Or some sort of structure preserving thing. So we decided to sort of focus ourselves on writing the functions that are obvious and then giving up on the ones where the implementation is not super obvious. Because those are going to require human thought anyways. And a machine, you wouldn't trust the machine to do that yourself. But if it's something stupid like concat or whatever, the machine should be able to handle that. The type is pretty obvious. So it can generally get a decent solution in like a second or so, but it depends on the problem and quite a bunch of other variables. There's probably some stuff we can do in refinery as well.
What about, I guess I also meant more broadly the way deduction and search is set up in refinery itself.
It's reasonably performant for the design space that we're in. The dependent subgoal stuff makes things hard.
Because it's opaque.
Yeah, and it makes it difficult to run things in parallel, essentially. But
would you want to figure out some applicative subgoal approach?
yeah, you could chuck another constructor in there, and that would totally work as well, or an applicative form of these tactics if you don't have dependent type theory. So that's definitely good space for future work, and would probably be a good use of someone's time. But yeah, this sucker here does make a lot of optimizations a little bit trickier. Where else?
Show this sequential tactics, and you mentioned that you can also try this or try that, right? Does this applicative / monadic GSL have anything that allows you to guide the search process, to guide it in the process, right, by assigning weights or scores rather than in the end analyzing the results that you have and comparing them to the best one?
I think that would require a different monad.
We actually do have some support for pruning the search tree. It took us quite a while to figure out, and I don't have it all paged into my head, and I've kind of forgotten how it worked. But basically, there's this. How did this work? There's these two combinators in refinery called reify and reflect, I think is what they are. And those allow us to do a decent amount of pruning, where we can sort of halt the proof search at a single point, take a look at all of our goals, and then sort of resume search. So we do have some support for pruning, but it is definitely a bit more of a advanced use case, and is a little tricky to get your brain around. I know it took me a couple of months to figure out how to actually implement it.
Right, and you can then assign, I don't know, weights to nodes or to edges, and then do some sort of a star.
It's not set up for directly.
Yeah.
Yeah, we do have support for it, and in theory you could do it.
Basically, just annotate your applicative or like monadic things with like some attributes, some guidance.
There's definitely search monads that let you do things like that. Absolutely.
Yeah. So I would totally encourage anyone to experiment around with these ideas. These are very fun to write. So that would definitely good space for future research. So does anyone else have any questions or comments before I move on? Or
you mentioned parallelization, like concurrency. How does it work?
That would be with the applicative.
Right. So if you have an applicative, right, then you just automatically run it in parallel?
I can point you some references offline if you want.
yeah.
Good writing about it. But there's some nuance to how you do that.
Yeah, especially once you start moving into the sort of dependent type theory land, which is what I think about most of the time. This dependent subgoal thing really does own you. So you have to be quite careful.
Nature there is kind of essential.
Yeah, it's pretty important.
I mean, or you get into basically meta programming your tactics.
Yeah, if you have tactics, yikes.
I mean, but if you want to introspect a dependent tactic, you'd have to do meta programming essentially.
Yeah, it's a tricky problem.
That gets recursive.
Yeah. Okay, so this is sort of how HLS works now, and this is how Refinery works now. If you want to use it, there's examples in the repo, and I would totally encourage people to try it out. But sort of where can we go from here? One thing to note is that not all of the tactics we have kind of fit well into this mechanical goal decomposition framework, right? So I sort of split them into two categories here. We've got the mechanical ones, like split, which splits a pair, or introduce, which introduces a lambda, right? And those are just like stupid, you know? Very obvious what to do. But using a variable is a little trickier, right? Like, which variable do we want to use? Projecting out of a record. Okay, there's kind of choices here, you know? Applying a function. There's all sorts of functions we could apply. There's sort of, we need a little intuition here. Or at the very least, some sort of brute force mechanical search. So they sort of have two different flavors. And this suggests that there ought to be some sort of distinction between these two modes of tactics. And if you're familiar with bidirectional typing, you're probably screaming at me right now, this is bidirectional typing. Here's bidirectional typing. And that's what we're going to do. We're going to split our tactics into two categories, checking tactics and synthesizing tactics. So a check tactic takes in a goal, and then we'll potentially call their tactics or whatever, and then we'll produce an extract for that goal, right? So this is split. We take a goal, which is the pair, we call two tactics to synthesize, or two check tactics to synthesize the each side of the pair, and then we produce the pair as the extract. Then we have synthesized tactics, which produce both an extract and the goal that it solves. So this would be things like variable lookup, right? If we're synthesizing, or we're running a tactic that uses a variable, we already know the type. It's the type of the variable. That comes from the context, right? Same thing with like applying a function. If we're using like an apply tactic, we already know the type that this thing produces. We don't need to continuously check against the goal to see, like, does this fit? Does this fit? Does this fit? So this gives us a very clear division in between sort of how the labor is divvied up. There's the labor that's done by the machine, which is these check tactics. And then there is the labor that involves the human or some sort of automated search procedure, which is the syn tactics. So how does this look like in code? Well, the formulation I have now is something that looks like this. So a check tactic is one that takes in a goal and can do some effects or whatever, and produces an extract. And the synthesized tactics are those that sort of produce both the goal and the extract at the same time. So split, as alluded to before, takes two check tactics, one for each side of the pair, and produces a check tactic. Use, which is the variable tactic, takes in a name, and then produces a syn tactic, because it already knows its type. You just look it up in the context, right? There's no real checking involved there. And then we have sort of an interesting tactic because it mixes the two modes, which is application. So you provide some tactic that will, synthesize a function type, basically. And then we know what that function is. We know its type because we synthesized it, so we can check it against the argument that we provide. And then, because we have this function type here, we've synthesized it, we can synthesize the output type. So this makes it very clear just sort of how the information flows, and also provides sort of a typed version of the tactics, whereas earlier we had sort of an untyped version. And I forgot to put it on these slides here, but there's ways of sort of going in between the two. If you want to turn a check tactic into a synthesized tactic, you need to annotate it. right? You need to provide some sort of type annotation to tell it, you know, what I'm going to produce. And if you want to turn a syn into a check tactic, you just synthesize, and then you check against the thing that you know, the goal that the check tactic gets in. So this is particularly interesting when we sort of stop thinking about proof synthesis and we start thinking about elaborators and proof systems. So for context, what is an elaborator? So for something like Idris, right? There's, or Coq or Agda or whatever. There's sort of the language that you type in, right? And then there's the core language of the theory. And the core language has a bunch of details that we like do not care about as the user. For example, like filling in implicit arguments, or, you know, oh, this construct expands this enormous thing over here. And you can use tactics to build these things. And if you're smart, you can do it in such a way that you never even need to write a type checker. You just check that all of your tactics are valid, sort of expose those as an abstract interface, and then say, well, if you build your program using these tactics, I know it's correct sort of because it's correct by construction. You only used rules that are valid. These rules always check the premises, so you're good.
The Isabelle Hall architecture, basically, right?
Essentially, yeah. Or LF style provers also do this. So this bidirectional thing, if you combine that with, you know, the approach of this, you know, just use tactics correct by construction argument, you get a really, really elegant solution, because all the information just sort of flows perfectly. You don't need, you get all the benefits of bidirectional typing, you know, with really cute algorithms, and everything becomes very simple and elegant. You kind of get type inference in a lot of cases for free, but for a proof assistant, for dependent types. And you can do a bunch of crazy stuff in the Elaborator as well, and not have it impact the core theory. So this approach is what we use in CoolTT, which is the theorem prover I work on with the authors from earlier. And it's an experimental type assistant, or proof assistant for cubical type theory, but there's a bunch of other cool stuff in there as well. So if you're interested in that, yeah, ping me after this, and I'd be more than happy to talk about it. But circling back, this bidirectional approach also solves problems for program synthesis. So one problem that you run into anytime you try and write a program synthesizer is you end up synthesizing a shitload of terms that are all actually secretly the same term, right? Like you might synthesize one version that's not Ada expanded and another version that is Ada expanded, right? Or you have all these like weird things that if you normalize them, they're all the same normal form. But that takes time, right? That's branches. That's extra search just to produce the same result over and over and over and over again. And then you have to pick one, which is even more time. So it's a bit of a mess. But if we sort of take this bidirectional approach into mind and only apply syntactics after all the check tactics have been exhausted, so decompose the problem down by doing all the stupid obvious things, and only then do you try and do clever things, we essentially restrict ourselves to only generating things in some sort of canonical form, because there's an ordering to how we apply the tactics. And in the same way that bidirectional typing also allows you to get sort of canonical forms with no type annotations, and non-canonical ones do require type annotations. This isn't without its perils. We generate kind of ugly stuff sometimes. So for this very stupid function that no one would ever write, we apply the introduce tactic because it's a check tactic. We apply the split tactic because that's a check tactic and we can apply it. And then we apply the synthesized tactics, which are project and then variable. And we end up with this very ugly monstrosity, which is not what the user would want to write. But I claim that this is sort of a non-issue because these programs, and they're called linters, and they're pretty good at solving things like this. So this would be an easy lint. Or if you have a normalizer, you just take it to a normal form. So for program synthesis, this is also sort of a useful lens to think about things. And I would encourage more people to, try this out. It works extremely well. And the, standard bidirectional stuff implies, introduction forms should be checked and eliminators should be seen. So in summation, tactics are pretty cool. There's still a bunch of stuff to explore. If you ever find yourself working on a type checker or proof assistant, do try this LF style bidirectional approach. It is really elegant. And it solves a lot of very concrete problems. And in fact, in CoolTT right now, we don't have a unifier. And if anyone's ever tried to write a unifier for dependent type theory, let alone cubical type theory, that's like a year's worth of work saved. And because of this sort of bidirectional setup, we can make a couple of clever moves and totally avoid the need for a unifier completely, which is, I think, is pretty cool.
What about, are you, even in the context where you might want like proof relevant unification? Because that seems like in some respects, it gives you a nice code book for what deduction rules you want in your unification. The Jesper Cox stuff?
So really what we mostly use unification for in proof assistance is sort of twofold, right? One is like figuring out implicits, saying, oh, this is uniquely determined by the context, just figure it out. The sort of Agda style if you write underscores everywhere, and then, you're done with your day. And the other one is sort of type class resolution, right? And the first one, you can solve with a cute Elaborator hack, where you can sort of shift in between like fibered and parameterized forms of type families. Talk to me later about that one. It's a bit involved, but
I thought it was also relevant for coverage checking and pattern matching.
Well, we program with eliminators.
Oh.
And there's another trick. There's some cubical stuff that you can use to kind of work around that problem as well.
Okay.
But that's still very much a, caution tape everywhere, work in progress. So I'm a bit reticent to talk about it in public. It's not totally done yet. But yeah, there is. I think there's a way to get around pattern matching without unification.
Okay. Eliminators suck, but it's a reasonable way to prioritize.
Yeah. I mean, the thing is you can program with eliminators, but only at the core level if you have a sophisticated enough elaborator that takes it to the eliminators, right? Like that, I think, is the approach that makes the most sense to me personally. Because having like case trees in your core language it's a bit hairy. And yeah, sometimes the eliminators show up in goals, and that's not great. But even in CoolTT right now, we have a sort of kind of pseudo pattern matching, which works pretty well. And I believe RedTT had something similar, just sort of the proof assistant that preceded it.
Depends on what your end soundness and engineering performance representation goals are too.
Mm-hmm, yes.
Like if you're like, yeah, so because at least if you want to have like a small trust kernel, compiling to eliminators form sounds totally reasonable, but that's not the representation you want to run at the end.
The problem is that with pattern matching, you immediately lose your homotopy interpretation. And that's if you want to do homotopy stuff, then you need eliminators.
There's a way around that though. In that, so one, there's matching that doesn't assume UIP, or where you can sort of in user space prove UIP for a specific data type and sort of require that there's a applicable proof in context to supply. Which I think is something that's like known in the folklore, but none of the current systems implement it that way. I could be wrong though.
Yeah.
Just it sort of creates a engineering concerns overflow for a lot of people working in the space.
Yeah, I mean, I definitely think there's space to be, or a lot of space to be explored, kind of design-wise, of handling, you know, H sets and H props, specifically with having sort of like local UIP or whatever. But yeah, it does present some pretty hairy engineering challenges. You want to do it right. So that's something I've also sort of been working on and tinkering with on and off. I don't have anything concrete to show for it yet.
Well, that's
Yeah.
the first step, having the question. So this is really awesome.
Oh, thank you. Yeah, no, I've been quite happy with how the bidirectional stuff has turned out.
So I guess one silly question is, like, for example, Frank Fenning has in all his various lecture notes, all these different sort of forward, like there's all these like different mini prover things for different logics. How, what can those different sort of little logics, sort of their forward or backward chaining processes be sort of examples in this refinery tactic stuff? Or like, what are some gaps in terms of types of deduction that you might not want to try and fit the refinery toolkit on?
If I had any criticism of refinery, it's that it's almost too flexible. And it's hard to...
You can't use refinery on refinery projects, you're saying?
Yeah. So even for things like, you know, linear logic or whatever, it's all about how you sort of construct those atomic tactics.
Yeah.
But
And what you're binding, and actually, this is getting into offline stuff that I was alluding to.
yeah. But we also do have a sort of state that you can thread through each of the...
So one thing, and Emily knows what I'm about to say, is when you're doing that proof search, you sometimes want both sort of an inner state of the current goal and sort of a persistent state across different attempts to reach goals, which I think ties into one of the questions that came up earlier, where you sort of learn and prune and retain that knowledge versus sort of the information you're manipulating currently.
Yeah, we have that. There's some S parameter that you can modify. And there's like a monad state instance for it. And that persists across sort of goals, but does not persist across backtracking.
So that would be the inner state.
Yes.
And potentially want a different state transformer on the outside for the persistent information.
Yes, yes. Or yeah, some sort of IO ref or something. Yeah, so that's something that you could do, because it is a monad transformer in the actual version. So you can cram a bunch of stuff in there. And it should just work fine. Yeah.
Do other people have questions?
Yeah, anyone else?
One thing I was wondering is, if you do this kind of thing with elaboration, can you get a kind of like some kind of hash consing for free where you kind of save things you've already elaborated and then use the same tactics again, so you get kind of, you don't have to recompile?
That's a good idea. I haven't thought about that. That would probably work, yes.
You
That's
have to
clever.
be careful about the that would be an example of that outer state transformer calendar, where maintaining an index, and it also gets into what variable binding representation you're working with. Like you might want De Broglie levels when you're doing that sort of work versus nominal, or some of those fancy nominal equivalence class things that unfortunately sometimes come with their own performance. You have to be careful about what your equivalence class decision procedure is.
Yeah. Sort of in CoolTT, we tie this with some NBE stuff. And yeah, you generally want to use levels for your sort of domain.
Yeah. So when you're or domain and other problems being when you're working on syntax, when you're writing normal interpreter or normalizing, used around indices, which are, or something similar, which phrased differently is variables are on a stack. And when you do a let, you're pushing on the stack. And this ties into another thing which some people might not be familiar with, but is intimately tied to what Reed's alluding to, which is normalization by evaluation, which lets you sort of reduce things, recognize when you don't actually, when you only have syntax for part of it, and then you can sort of have these augmented values that you can transform back into syntax. Just in case most people don't know, someone doesn't know that.
Yeah, I mean, that's like a talk unto itself. You could do
hours
and hours and hours on NB.
Talon, you have to be careful about the sharing, like the overhead of the sharing and what the term size is. Like, you will save space, but ultimately you're then also asking what's the typical program size and sort of what constant factors that introduces. For large enough things, I mean, at some point it turns into you're doing a database of terms and goals. And how are you maintaining that across runs, almost? So like, it turns into having a little database query thing for persistent knowledge, depending on how you spin it. That would be the over-engineered general purpose version. Oh, and yeah, I definitely have some thoughts on that you might like, that actually tie into some of the architectural choices for how you would integrate with LSP that we can talk about later too.
Yeah. Yeah, because right now my thoughts have been you just sort of hook directly into the elaborator and just have that talk to something as it's elaborating. And I think it's a pretty lightweight way of doing things that doesn't involve like basically building a database inside of your proof assistant, which sounds hard.
Well, I mean, it will be a database no matter what. I mean, no matter how you slice it, the moment you're doing persistence, even within a session, it is a database. It's just not with the administrative burden. I mean, that's what packages and local builds are. And in the same sense, any hash consing strategy, you have some scope of whether it's in the current sort of proving system or set of packages. Like there's a question of how do you namespace your hash consing of proofs.
Yeah. Yes. Yes.
But like, and then it gets into things where you almost then need a renaming tactic because some of these things might refer to equivalent things that are actually defined in different spots that you may not want to deem equal. Or maybe you want to use the thing that I keep on thinking homotopy type theories for, which is I have an equivalent implementation on an equivalent structure. I should just use that. But
Yeah.
it's not quite, homotopy type theory isn't quite about that, even though if you don't look at it too closely, it almost seems like it's about that.
I mean, you can use the structure identity principle, and Carlo Anguli has some stuff recently. I'll see if I can find it. But that's exactly about this. But yeah, more broadly, cubicle type theory does give you a lot of options for sort of controlling modularity, which is a bit of proof-assistant sort of lore that I think is, or design, I would say. It's been kind of overlooked in favor of fancy type theories. Because proof assistants are sort of inherently anti-modular, right? Like the sort of blessed path is that you design your definitions beautifully and just right so that everything falls out by definitional equality, right? But then if you want to tweak your definition, everything breaks because everything's based off definitional equality. So then
You should read Adam Chapala's theorem proving book. He shows how to not do that by just having his crazy tactics.
yeah, I think there's another way of doing it that doesn't involve violent amounts of proof automation, which is sort of, you have a means of exposing certain definitional equalities to the outside world, and only those, through some sort of fancy module system. And this, it feels like a nice counterpoint in between the point, like the lean approach, which is we pretend definitional equalities don't exist, and we say using them is bad style, and we just use synth tactics everywhere. And the sort of Agda approach, which is definitional equality is great, just do whatever you want with it. It feels like there's got to be some point in between those.
I guess one stress test I always think about in my head that I haven't actually worked through, but I think ties into what you're saying or alluding to, is sort of there's the whole combinatorics proof by bijection kind of approach where you sort of exhibit an isomorphism between two different classes of combinatorial objects as sort of like a tractable but still non-trivial stress test for some of these equivalences. Where like you're sort of showing the cardinality of two combinatorial objects are the same, and you know one, therefore you get the other through some bijective process. We can talk, but again, that's like an offline thing.
Yeah, for sure. Yeah, so any further questions, or does all of this make sense to everyone? I don't want to leave anyone walking away from this totally scratching their heads being like, I didn't get a single thing.
The dumbest questions are the most fun questions.
Exactly. I love questions like that. They're super
They're kind of
great to answer, and a lot of times clear up a lot of confusion.
All right. So sounds like no more questions. So I want to thank both Reed and Shay, our speakers tonight, everyone joining us online and everyone joining us here. Hopefully we're going to be having more of these again in the future, so much more frequently than between our last two.
and a quiet year or so.
Yeah.
Public
For
health
anyone that wants to
emergencies.
hang
we do
out
that.
and have some more food and drinks and socialize.
Is there a restroom nearby?
Yep.
On this floor? Okay, cool.
And yeah, that's everything. We got a recording of Reed's talk that we'll be sharing online soon. And yeah, also if anybody wants to speak in the future, feel free to reach out to me through the app or other means, and we'd love to have you talk. And that's all. Thanks, everybody.
Yep. Thanks for organizing. Have a good night, all.
That's cool.
That's very cool.
Yeah. One of my takeaways was the next time I implement like a little tiny land like this, I can try to write a tactics thing for it, so I can just like auto generate little randomly calculus expressions.